Welcome to this deep dive. Today we're tackling a question that feels, well, almost childlike, doesn't it? Why is the sky blue?
It does, but it's fundamental.
Exactly. And we're going to unpack it, reveal the really quite incredible physics happening, every single day right above our heads.
Yeah.
It sounds simple, but believe me, the answer has some unexpected twists.
Yeah, and our mission today really is to give you a clear path to understanding this. It's a universal thing we all see.
Right.
And getting a handle on these fundamental aspects, moving beyond just noticing it's bright outside to understanding the interactions, well, it just deepens your appreciation, your knowledge.
Okay, let's get into it then. We have to start with the absolute basic element here. Light. Sunlight. So imagine the white light coming from the sun. Think of it like a team, maybe a team of different colored runners all bunched together.
Okay, like a race?
Sort of, yeah. When they run together, side by side, they just look like, well, white light. But individually, each runner is a distinct color. You've got red, orange, yellow, green, blue, indigo, violet, all of them.
That's a good way to put it. White light really is all the colors of the rainbow, just combined.
Right.
Now, here's where it gets interesting. Each of those runners, each color has a different, let's call it a stride or wavelength in physics terms.
In stride, okay.
Yeah. So red light, for instance, has a very long stride. Imagine a giant taking these huge long steps.
Okay, lumbering steps.
Exactly. But blue and violet light, they have much shorter strides, like a tiny, quick-footed runner taking lots and lots of small, rapid steps.
Ah, I see. Big steps versus quick little steps.
Precisely. And how these different strides, these wavelengths, interact with what they encounter, that becomes absolutely critical.
So we've got this light, this team of runners with different strides heading towards Earth. And what do they meet first?
The atmosphere.
Our atmosphere, which we can think of as this huge invisible blanket of air wrapped around the planet, right?
Yep, our gaseous envelope.
And it's made up of these incredibly tiny bits, mostly individual molecules of gases like nitrogen and oxygen.
Primarily, yes. About 78% nitrogen, 21% oxygen.
Plus some other stuff like tiny bits of dust, water vapor, other minuscule particles. But the main thing is these gas molecules are tiny, like way, way smaller than even a grain of sand.
Oh, absolutely minuscule on that scale. Individual molecules.
So the question then becomes,
Right. What actually happens when this incoming sunlight, this team of light runners, hits these tiny, tiny bits in the atmosphere?
this is where the magic happens, isn't it? Where the physics becomes visible.
It really is.
So when sunlight enters the atmosphere, these light waves are runners. They start bumping into these tiny gas molecules.
An encounter.
But it's not like a hard bounce, is it? It's more like the light gets scattered.
Scattered, exactly. That's the term physicists use. Think of it maybe like the light wave gets knocked slightly off course.
Like in a pinball machine. Or maybe navigating a really crowded room.
That's an analogy. It hits a molecule and gets sent off in a completely new direction. The light spreads out. That's scattering.
Okay, scattering. But here's the crucial part, I think. Go on.
Not all the colors scatter the same way.
Yes. That is the absolute key. This is what explains the blue sky. It's called Rayleigh scattering, after the scientist who described it.
Rayleigh scattering. Okay.
You see, the tiny gas particles in our atmosphere, the nitrogen and oxygen molecules, they happen to be just the right size to interact much more strongly with the shorter wavelengths of light.
The shorter strides, the blue and violet light.
Exactly. They scatter the blues and violets much, much more effectively than the longer wavelengths, like red.
So it's like, if you're trying to weave through a dense forest of thin poles,
Yeah.
if you take tiny quick steps, you're going to bump into those poles constantly, right?
Yeah.
Get deflected all the time.
You could bounce around a lot.
But if you're taking giant strides, you might just step right over many of them. You'll go straighter.
That's a fantastic way to visualize it. The short stride blue light bumps and scatters off those air molecules way more often than the long stride red light, which tends to just keep going.
Okay, so connecting that back, as the sunlight pours into the atmosphere,
That blue and violet light, with its short stride, hits those tiny air molecules and just gets bounced and scattered everywhere, way more than the reds and yellows.
it really does. It gets scattered in all directions, bouncing from molecule to molecule across the whole sky.
So what does that actually mean for us looking up?
Well, think about it. If that blue light is getting scattered randomly in all directions, then no matter where you look up in the sky, some of that scattered blue light is heading straight towards your eyes.
So you see blue coming from everywhere overhead.
Precisely. And that's why the sky looks blue. The other colors, the reds, oranges, yellows, greens, they aren't scattered nearly as much.
They just keep going straight.
Mostly, yeah. They pass more directly through the atmosphere to reach our eyes. Which actually also explains why the sun itself looks kind of yellowish-white.
How so?
Because some of the blue light has been scattered away from the direct path. What's left in that direct beam from the sun is the combination of the remaining colors slightly less blue, making it appear a bit yellowish.
Wow, okay. That makes total sense. But hang on. If blue light scatters so well, what about sunsets or sunrises? The sky turns red and orange then. Why isn't it blue?
Great question. It follows directly from the same principle. Think about where the sun is at sunrise or sunset.
It's low on the horizon.
Right. So the light from the sun has to travel through much more of the atmosphere to reach your eyes, doesn't it? It's taking a longer path through that blanket of air.
Okay, a longer, more crowded obstacle course.
Exactly.
Yeah.
And because it's traveling through so much more air, encountering so many more of those tiny scattering particles,
Almost all the blue light gets scattered out.
you got it. By the time that light reaches you, nearly all the blue and violet light has been bounced away, completely out of your line of sight.
So what's left?
What's left are mainly the longer wavelength colors that didn't scatter as much, the reds, the oranges, the yellows. They make it through that long journey.
And that's why the sky near the setting or rising sun looks so, warm and fiery.
That's precisely it. More atmosphere means more scattering, removing the blues and leaving the reds.
Okay, one more then. Clouds. Clouds are in the atmosphere too, right? Why aren't they blue? They're usually white or gray.
Good point. This comes down to particle size again, if we connect this back.
Okay.
Clouds aren't made of tiny individual gas molecules like the rest of the clear sky. They're made of much, much larger particles.
Like what?
Tiny water droplets or little ice crystals, much bigger than a nitrogen molecule.
And bigger particles scatter light differently.
They do. This different type of scattering, called scattering, happens with these larger particles. And the key thing is these larger droplets scatter all the colors of visible light, red, green, blue, everything pretty much equally.
Not favoring the blue like the tiny air molecules do.
Exactly. They scatter all colors, roughly the same amount in all directions. And when you scatter all the colors of the rainbow equally, what do you get?
White light. Because white light is all the colors combined.
Bingo. So clouds look white or sometimes gray because they're scattering all the sunlight's colors equally back to your eyes.
It's honestly, it's quite amazing how a question that seems so simple, why is the sky blue, leads you down this path involving light waves, tiny molecules, different kinds of scattering.
It's a beautiful example of everyday physics.
It really is. So the next time you're out and you look up at that beautiful blue sky, maybe take a second. Think about those tiny, quick-footed blue light waves just dancing and scattering their way through the atmosphere to reach you.
Makes you appreciate it in a new way, doesn't it?
Definitely. It makes you see the world a bit differently.
And, that leads to a final thought, maybe something for you to ponder. How many other things that seem completely mundane, completely normal in your daily life might be hiding equally fascinating, equally profound scientific explanations just beneath the surface, just waiting for you to ask why and take a deeper look?
That's a great point. Keep that curiosity going.
Absolutely. Keep observing, keep asking why. The world is full of these hidden wonders.